Set. All right, so I think it's time to go. Did you hit record?
Yep.
Okay. And I trimmed the beginning so I can make embarrassing jokes. So at the beginning. But then when I start, then I have to stay on point. Welcome to the second meeting of mus420A. So today we're going to look at the first assignment, which is hopefully a lot of fun. It's partially just touching base on prerequisites and partially getting you up to speed on the lab environment, which is C++. We'll still do some MATLAB, but you know this is my C++ course where we really look at some classes. And the good news is a lot of great classes have been written for us. So another big function is getting familiar with some of the great stuff that's already done. The synthesis toolkit, started by Perry Cook and maintained nowadays by Gary Scavone at McGill. It's a really fine collection of classes that you can consider to be good reference implementations in this area, in the area of audio effects and digital synthesis that are using the kinds of techniques we're talking about and beyond. There's much more in there. So let's begin with the, and then finally I'll go into some overview of research. It's mostly research here that is in this area. As I mentioned, this is a course that's designed to sort of get people ready for research in this area and also make them aware of the research in this area. So here we are at the Karma homepage, and just to remind you, you can just go to the homepage, then go to the weekly schedule, and then you're there as to what's going on. So this is what we did last time. We talked about the physical modeling overview, and we did a little bit on the demos side, and we mentioned a lot of this stuff. Spent most of the time just going through this documentation, this particular file. So now, if you see here, there's a new thing. There's a new lecture video. That's the overview of physical modeling that we did on Monday. And then this is also new, the first exercise. And so here it is in PDF. And so here's the theory, basic, prerequisite checks, and maybe extension a little bit. I mean, we talked about the Laplace transform last quarter, but we didn't do a lot with it, and we tended to use it to just turn derivatives into powers of S. But here it is, the actual definition, and we want to derive the differentiation theorem. And so it's a basic exercise, and it's also a very important theorem. So we want to really understand that. It doesn't hurt to see it a few times. So then we have an application of the Laplace transform to Newton's law, F equals ma. So we've all heard F equals ma. Well, that's an ordinary differential equation. Force is mass times the second derivative of position with respect to time, or the first derivative of velocity with respect to time, or acceleration. So F equals ma, F equals mass times acceleration. And so this is going to take you through some exercises associated with that. So we find the transfer function of just a mass. So what do you do with a mass? You push on the mass and then it moves. And so we imagine that it's on a frictionless surface, it's in a vacuum, there are no other forces, everything's ideal. And so the force then, you can divide it by m and integrate it twice and get position. And more commonly, we will divide the force by mass and integrate once and get velocity. It turns out that the two variables that are really nice to work with in this world are force and velocity. And one reason is to say that if you divide the force by the velocity, you get impedance. It becomes just like a resistance. So it's very much an analog to circuits, which is a little bit funny because circuits are analogs to this. So the term analog circuits really refers to the circuit modeling things like masses and springs and dashpots. But it depends on where you start as to which one is an analogy for which. Okay, so then we'll do some review really of last quarter, which is, we get our transfer function, we find the poles and zeros, we find the frequency response. So you can say this is a bit of review, but it's applied in a physical modeling context. Because now we've got a transfer function that's actually a physical object, it's a mass. And its transfer function is what? It's the position over the force. So it's not an impedance, it's not an admittance, but it's a transfer function nevertheless. And you can choose, when you have a physical system, you can choose any point as an input, and you can choose any other point as an output, and get a transfer function between them. Furthermore, at each of those points, you can arbitrarily select units. You can say, I want to think about the force that's coming into this. I want to think about pushing on this input. But you could also say, I want to just set the velocity. I'm going to contrive a velocity source, and I'm going to have a velocity input. And you can do it. You can work with it that way. So you choose your positions of inputs and outputs. You choose your units that you want to work in. And as I mentioned, the most common are force for input, velocity for output. And then you compute your transfer function. So if you do have a force input and a velocity output, your transfer function is V over F. That's an admittance. So it's 1 over an impedance. So the most typical transfer function in physical modeling is an admittance. You push, you get a velocity, and you've got an admittance as your transfer function relating the two. Okay, so that's that, and that's theory, review, and extension, and then we have our lab. And so the lab is the getting familiar with the synthesis toolkit, and so you basically download it and install it, and do some very simple exercises. This first exercise makes the audio probe program, and then you run it, and it prints out all the sampling rates you can use. It's a nice little utility. So if it turns out that you only have a particular sampling rate that you can use, then you may have to set it. And so in your program, you may have to call STK set sampling rate in order to get it. For example, on a Unix machine, most of the Unix machines around Karma are at 48 kilohertz by default. So you have to actually change the code because the default in the SDK is only 44.1. And on the Mac, that's right, but on the Linux machine, you need to set it. Unless you're on hardware that'll support either. If your hardware supports 44.1, just go with it. But be careful, because sometimes you get sampling rate conversion when that happens. So sometimes hardware will, a system will seem to support all sampling rates, but it's actually doing software conversion. The Mac is pretty good about that, actually doing that. But that's more work on your processor, so you should be aware of it. And then there's a little example, which is the sine oscillator. So you go there and you play it. And now it's good to have SOX installed, SOX. And if you have that, then you can just say play without running this little utility in the SDK. And if you do want to resample, then you can do that. This is in the SND file. SND file resample will sample to any sampling rate and do it kind of offline separately. So if you need to do that, it's there. Yeah, so here's SOX. So if you have the SOX distribution, then you can just say play. Okay, so that's basically kind of the warm-up on the SDK, and let's see if I can expand this out. Does that fit okay? Nice. And then for just opening up audio files and playing them, my favorite is Audacity, but anything you have will do. You may have Adobe Audition or whatever. There are a lot of good programs out there. But the best free one that I know is Audacity, and it runs on Mac, Windows, and Linux, so you can run it anywhere you are. So then here's the assignment. It's very simple. You just unpack, you download and unpack, look at the README file, and then do a couple of tests, and then you just modify one case. So there's this file echo.cpp, and so you just modify it. It's a trivial modification. It's just something to force you through all the steps of downloading and getting it working and so on. So it's a real simple lab. But if you have some extra time and you want to play with it, then here's some ideas, because it will do real-time signal processing, so you can hook up a microphone and have some fun with it. So there's some suggestions there. And so now this exercise is nominally due next week, but please keep track of your time. I want to know how much time you're spending. This is a 3-unit class, not counting the special project, if you do a project. And 3 units should be only about 9 hours of time a week, maybe 10, And so 3 of those hours are in class, whether you attend personally or watch the videos. And that leaves only 6 hours for everything else, 6 hours for your reading and your homework problems and your lab, everything. So That's theoretically how much time this course should demand. And then if you have a 1-unit, fourth unit project, then that's another 3 hours a week of effort, on average. You average these things. So if your time is significantly beyond 6 hours, let us know, because we have a nice small class and we can adjust the pace of the class to fit the students very well. And so let's say it takes 8 hours, then I'll shave down the next week's assignment and try to come in under budget. If it's looking like 12 hours, then we'll just extend it to a 2-week assignment, right? So we want to right-size this stuff. And the rationale is, if you're taking a 15-unit load and every unit is demanding 3 hours per week, like it should demand no more than, then you're talking about 45 hours a week of focused work. We're talking about billable hours. Really, this is not just goofing around and checking Facebook. This is really getting stuff done. So when you distill it all down, and you've got 45 real hours going on. The general rule of thumb that I hear is that it's about a 2-to-1 thing. That in industry, people work about half the time, maybe a bit more. But so that means that's already a 90-hour work week, fully loaded with water cooler time and so on. So 45 hours is a lot, and so I think that we should strive to not exceed that as class organizers, because we don't want to destroy people's balance. People should be able to learn and live and thrive. So give us that feedback, please. All right, so on to the next. What happened? Oh, yeah. Yes.
Sorry, I should poke it periodically.
Yeah, I just need to set the timeout longer, I think. So then we just hit this button once.